Greeting, ladies and gentlemen. Today video I'm gonna re-explain again about question number 2 because one of our friend cannot see the answer that I'm right in the previous video, so I need to rewrite it again and remake it again. But anyway, question 2, there is under a normal operating condition, the electric motor exerts a torque of 2.8 kilonewton meter on a shaft AB. Knowing that each shaft is solid, determine the maximum shearing stress in A. shaft AB, B. shaft BC, and CD. Given the reference answer, that will be this value. Now, first thing first, if I attempt to answering this question, we need first to draw the FPD. I'm assume that this motor will rotating in the direction of, if you take a look in this direction, in this point of view, the torque will exert downward direction produced by the motor. If you take a look in the side view, the motor will rotating in the anti-clockwise direction. But if you take a look in the front, in this direction, it will have a direction of torque downward direction. Because if you take a look in the side direction, it will be like this. It is the shaft, and the motor rotating, I'm assuming, rotating in this direction. So if you take a look in front, then the torque will exert downward direction, which is in this direction. So that's why I'm making cross section. There is a torque that exerted by the motor downward direction. The question asking what is the determine the maximum shearing stress. Now I'm gonna use the shearing stress due to torsion formula. So we'll have an internal torque exerted by the motor, since that the analysis were made at point A to point B, which is involve the torque exerted by the motor. So torque exerted by the motor times by C, it is the distance from the origin to point of analysis, and over by J. J is stand for polar moment of inertia. Now, the internal torque, that will be 2.8 kilonewton meter. In this equation, you need to concern about internal torque, not an exerted torque. In the equation, it been given 2.8 kilonewton meter on shaft AB. The motor exerted. This is the torque that been exerted from the motor on the shaft. But in this formula, we were using internal torque. It will have a same magnitude as 2.8 kilonewton meter by the electric motor, but in a different direction. It is mean if the motor were exerted torque in downward direction, so it will have internal torque in the upper direction, but the same magnitude. So that's why you will have a 2.8 kilonewton meter, but in a different direction of torque. And the value of C in this question is referred to the radius for the shaft. For example, if you take a look at the shaft AB, you will have a cross-section area. It's like a circular, so you will have an origin. Now, the point of analysis is from the origin into the very outer of this shaft. In the other word, or simple term, we call it as radius, because determine the maximum. The word maximum is refer to the maximum point that you will get. So as the old system were operating, the outer area of the shaft will burden by the highest maximum shearing stress. So that's why we were taking a point of analysis at the very outer of this shaft, which is as example in there. So it's just as simple to say that the value of C is just a radius of this shaft from the origin, because it's asking a maximum shearing stress. It needs to make an analysis at the very outer of the shaft, because at this point it will occurs the most highest maximum shearing stress. So the value of C, it is just as simple as the radius of this shaft. You need to divide 56 millimeter in here into 0.028. Then you need to convert it into meter, because we were dealing with SI unit in the form of kilonewton meter. So you need to convert it in meter into meter, so that's why you will get 0.028 meter. Now the value of J, or polar moment of inertia, is dependent on the shape that you were dealing with. Since that we were dealing with a solid shaft, so the polar moment of inertia, that will be pi over by 2 C the power of 4. The value of C, as you may guess, the value is just the same as 0.028 meter. So the value of C for the polar moment of inertia is sharing the same value for the C in the upper side of this formula. So you can simple this equation even more into this one by cancelling out the value of C in the upper side by the below. So we will get tau prime over by P over by pi over by 2 C the power of 3. So now you need to insert the datum. Then you will get 81.2 megapascal. We proceed to the second question, asking about the maximum shearing stress at cross section B to C. So you need to make an FPD from point A to C, from here to there. So this is the cross section that I made. You will have a 2.8 kilonewton, the internal torque, because we were dealing with internal torque, so that's why you will have a direction of torque from the motor. Upper direction is come from the internal torque that we defined just now, 2.8 kilonewton exerted upward. You will have an another internal torque, maybe 1.4 kilonewton exerted downward direction. At the shaft BC, it will have an internal torque also that defined from the equilibrium of 2.8 kilonewton by 1.4 kilonewton. So you need to divide 2.8 kilonewton, since that it have a different direction than 1.4 kilonewton. Thus you will get 1.4 kilonewton exerted upward direction at shaft BC. So you will get 1.4 kilonewton for the value of internal torque for BC. You times it by the value of C, since that is sharing it's not sharing the same radius, so you need to divide 48 by 2. So you need to convert it into meter. Thus you will get 0.024 in the form of meter. We divide it by pi over by 2. The value of C you need to power by 4. Thus you will get 64.5 megapascal. And again, the value of C in the downward side, in the downside, is just the same as the upper side. Now let's bring our discussion into the last question, which is shaft CD. So you need to make an cross section from point A to point D. There is the FPD, so you will have a 2.8 kilometer produced by been given by internal torque. From motor, you will have a 1.4 kilometer meter been given by equation exerted downward. As you take a look in this point of view, you will exert downward direction. You will have another torque that have a magnitude 0.9 kilonewton meter downward direction, and you may guess by now you will have another internal torque at CD. So this internal torque we need to define it is just simply as equilibrium of this other torque. So this means 2.8, you need to minus it by 1.4 kilonewton, minus by 0.9 kilonewton. I'm assuming upward direction as positive and downward direction as negative. So there you can have it 0.8 kilonewton meter minus by this magnitude. So you just simple the equation, cancel out the value of C at the upper side to the below side. Then since that you'll have a diameter about 48 millimeter, you need to convert it into meter, divide by 2, you will get 0.04 for the value of C, and you will get 23 megapascal. So I think that's all for today. Thank you for watching. If you did have any advice for me, please do so. You can do so. It will be my pleasure to have it. So thank you for watching and have a nice day. Bye bye.